Hi, welcome to the discussion on techniques in biology and biochemistry with course code Sbl1023. Today we're going to look at the topic 6, which is on titration. I believe that you have carried out the experiment on titration in your laboratory session. And in this online discussion, we will be looking at the principle behind the experiment, which is titration, that you have carried out. The outline of this chapter will be on titration principle, titration of strong acid, titration of monoprotic acid, and titration of polyprotic acid. Before we look at the principle behind titration or the theory behind titration, we shall look at the experiment set up for the titration, which is on laboratory number 3. The experimental setup for a titration experiment will look something like what is being shown in this diagram. The apparatus that is involved is or are burette, conical flask. And titration usually involve usage of acid and base. In a titration experiment, usually the base solution is added into the burette, while the acidic solution is added into the conical flask. The base solution that is added into the burette is called the titrant, while the acidic solution that is contained in the conical flask is called the analyte. This is a typical experimental setup for a titration experiment. In general, there are a few different types of titration experiment that could be carried out. The first is between a strong acid and a strong base. A strong acid and a strong base example is being shown in this slide. The example of strong acid that is being used in this instance or in this example is hydrochloric acid, and the example of strong base is sodium hydroxide. I believe that you have learned in your secondary school in your chemistry class regarding the reaction of acid and base. Acid, when added together with base, it will give rise to the product which is salt and water. What I have been mentioning to you just now, or what I have been describing just now, is the basic chemical reaction between acid and base. Now we look at the second and third type of titration. The diagram and chemical reaction that is shown here on the left side is between weak acid, which is the acetic acid, react with strong base, which is the sodium hydroxide. And the chemical reaction as well as the diagram that is shown on the right side of this slide is titration between a weak base, which is ammonium hydroxide, with a strong acid, which is hydrochloric acid. Okay, before we look at the titration in detail, there are some principles regarding the titration that you should know. The first concept that you need to know regarding or related to titration is Ka, or which represents acid dissociation constant. Acid dissociation constant, or Ka, has no unit. The usage of this Ka is used to distinguish between strong acid from weak acid. Theoretically, strong acids such as hydrochloric acid and nitric acid both have higher Ka value as what is being shown here. On the other hand, weak acids such as acetic acid is having lower Ka values. Why does strong acids such as hydrochloric acid and nitric acid have high Ka values? It is because both acids dissociate more when dissolved in water comparatively to acetic acid. Acetic acid, on the other hand, does not dissociate well when dissolved in water. And now I'd like to highlight the second very important aspect in titration, which is the equivalence point. What is equivalence point? Equivalence point is defined as the point in the titration experiment at which the acid is exactly neutralized. Now we try to search for the equivalence point of a titration experiment between a strong acid with a strong base. The equivalence point could be determined by looking at the titration curve. A titration curve usually shows the scale of all the variables of pH on the y-axis and the volume of base added in the x-axis. This titration curve is generated when the experimental setup of the titration process, in which the acid is being contained in the conical flask while the base is being placed in the burette. Okay, now let us look back at the equivalence point. The equivalence point of a titration between strong acid and strong base will always equal to 7. 7 here, the number represents the pH. Okay, now let us look at the second example, which is the titration between a weak acid with a strong base. This is the titration curve that is generated by the experiment. You can see that in this diagram, the equivalence point that is generated between the titration of weak acid and strong base is always above 7. And we try to look at the third example, which is the titration experiment with using a weak base, which is ammonium hydroxide, with hydrochloric acid, which is an example of strong acid. The equivalence point that is shown by the titration curve is or will be below 7. In the experiment that you have conducted for laboratory 3, you need to generate or derive with the titration curve of pH against the volume of base that you use in order to determine the equivalence point. And in your laboratory manual, there are instructions that is being shown to you, and you are required to calculate the changes of pH over the changes of the volume. And you are required to plot a graph of changes of pH over the changes of volume over the volume of sodium hydroxide. And in this second graph, you can actually determine the volume where equivalence point occur. The volume that is shown here is exactly at 25 ml, where the equivalence point is located. In other words, when 25 ml of sodium hydroxide is added into the acid, the equivalence point will be reached. Please bear in mind that the molarity of weak acid and the molarity of the strong base that is used in the titration experiment is 0.1 molar. You can refer to the laboratory manual for more information regarding the experiment procedure. To summarize, the titration of strong acid and strong base, or the titration between strong acid and strong base, the equivalence point will always at 7. On the other hand, the titration of weak acid and with strong base, the equivalence point will be above 7. And the last type of titration, which is between the weak base and a strong acid, the equivalence point will always be below pH 7. This is the rule of thumb that you should remember. After the volume of sodium hydroxide of the equivalence point is determined, the next step will be determining the pH of the equivalence point. How you do that? Okay, first of all, what you need to do is that you need to draw a line from the equivalence point volume of sodium hydroxide into the titration curve, and the value of pH which is adjacent to the straight line will be the pH where the equivalence point occur. The pH of the equivalence point that is estimated from the titration curve is approximately or around 8.5. This means that at this point, or at this pH which is 8.5, all acid is exactly neutralized by the sodium hydroxide or by the base that is used. Okay, now we look at pKa. What is meant by pKa? pKa of an acid is determined by the relative strength, or it is the degree of dissociation in water to produce hydrogen ion or hydronium ions. How do you calculate pKa value? pKa value could be calculated by using this formula. This formula is also known as Henderson-Hasselbalch equation. Now we try to look at one example of the calculation. Assuming that you wanted to know the pKa value of acetic acid, and the information that you know is the Ka value or the acid dissociation constant value of acetic acid, which is 1.74 times 10 power of negative 5. Using the Henderson-Hasselbalch equation, replace, which is shown in here, replace the value of Ka with the exact value and solve the mathematical problem, and you will derive with the answer of positive 4.75. Positive 4.75 is the pKa value of acetic acid. A positive pKa value indicates that the acid does not actually ionize fully in water. Here we try to compare the pKa value of strong acid. Two examples is being shown here. The first is hydrochloric acid. The pKa value is negative 6.3. And the second example of strong acid is the nitric acid, having the pKa value of negative 1.4. Strong acids such as hydrochloric acid and nitric acid have more negative value of pKa. Negative value of pKa means that they almost 100% ionize in water. pKa could also be determined by looking at the titration curve. Half of the equivalence point is where you can find the pKa value. The titration curve shown here is an example of titration between acetic acid and sodium hydroxide, and the pKa value that is observed by the titration curve is approximately 4.75, which is almost exactly the same as what we have calculated from using the Henderson-Hasselbalch equation. In other words, at pH 4.75, the acetic acid, which is in solution form, started to ionize, and it can react with the proton that is released by sodium hydroxide. The acid-base reaction will continue until it reaches its equivalence point here, in which all acid is being exactly neutralized by the base.